Okay, so the second part of this chapter, calorimetry, we are going to discuss change of state. Now, in change of state, if a solid is turning into liquid, that will be called as melting, and liquid turning into solid, that is called as freezing. Solid turning into gas, that will be called as vaporization. Just a minute. A gas turning into liquid, that will be called as condensation. Solid turning into gas directly would be called as sublimation, and gas turning into solid directly will be called as solidification. You should be aware about the names. And now what we are going to do is discuss about the process. Okay, so let us take an example of water. Now in water, what we have is, the molecules which are there are at a certain distance. Okay, so these molecules at any given time are vibrating. Okay, the atoms and molecules are in constant state of vibration. That gives kinetic energy to them. Also, the molecules attract each other with a force, that is the intermolecular force that they have, and this will give potential energy to the water molecules. Okay, now say for example you are withdrawing heat from it. The heat has been lost. So what will this heat do? Okay, the lost heat will reduce the kinetic energy, and also it will reduce the potential energy. So say for example water, which is at 10 degrees Celsius, gradually the temperature will drop to 0 degrees Celsius. And while the heat has been taken away, the kinetic energy as well as potential energy is lost. Now when water, which is at 0 degrees Celsius, okay, if it continues to lose heat, so what will happen? That is very important for you to understand. So water is at 0 degrees Celsius, okay, and water is losing heat. Now when water is losing heat, the temperature will not change. It will continue to remain 0 degree. But what will happen is the separation between the molecule will reduce, and the molecules will come little more closer than they are. Okay, so in this process, 0 degree water will change to 0 degree ice. So what you need to understand is when water reached 0 degree, it continued to lose heat, but that heat was not altering its kinetic energy, but it was altering its potential energy. It was bringing water molecules closer till there is a change of state, and that is turning into a solid, which is called as ice. If you continue to lose heat, okay, ice continues to lose heat, then the kinetic energy of ice will continue to be less, and the temperature will be further less. Okay, the temperature from 0 degree ice, it can go up to like say whatever -5 degree ice. So you can continue to lose heat and continue to reduce the kinetic energy. If you are doing the opposite, that means if you take a container and you have a burner over here, okay, there is a flame, so heat has been supplied, and in this if you take ice now, okay, so this ice is taken. Now let's say this ice is at -10 degrees Celsius and you're heating it. So the process is, first you will get ice at 0 degrees Celsius. From -10 you will get it at 0 degree. Heat is taken, okay, heat is used. Then again you supply heat and you will get water at 0 degrees Celsius. Okay, so remember the temperature didn't change, from 0° ice, you got 0° water. And then if you supply heat, you will get water, say at 10°C, or if you continue to supply heat, it will continue to heat up. Is that clear to everyone?
Yes,
Okay.
sir.
Now, what I explained you earlier, if that has to be shown over here. So this is temperature, okay, that is degree Celsius, and this is time, okay, which is seconds. So earlier water was at 10°. So then you have a graph which will be like this. Okay, so here you have A, B, C, and D. So what does AB indicates? AB indicate the temperature of water going down from 10°C to 0°C. What does BC indicate? BC indicate water which was at 0° changing into ice at 0°C. What does CD indicate? It indicate ice which is at 0° going to, like, say -5°C. So this can be termed as -5. So students, this is what is called as a cooling curve. Okay, it is called as a cooling curve. Now this cooling curve is there in the syllabus. But if you do it for this one, what I explained over here, where again the same thing, this is temperature, which is degree Celsius. It's not difficult to understand, but this part is not in the syllabus. This is seconds. So say for example, this is -10°C, this is 0°C, and this is 10°C. So first thing, you're bringing ice from -10 to 0. Then you are making it ice to water, and then water which is 0° to 10°. So this is called as a heating curve. Okay, so heating curve is not a part of the syllabus, but a cooling curve, they can ask you questions. They may ask you to draw it. They may ask you to ask questions based on that what is happening in BC. Okay, so you should be able to answer that in BC there is a change of state happening. Also, if you notice at BC, there is no change in temperature. How do you know that? It's a horizontal line. Whenever there is a line which is inclined, the temperature corresponding is going from 0°C to 10°C. Okay. So far what we have done what are the different change of state known as. We have seen what exactly happens when there is a change in state. The separation between the atoms and molecule vary. Okay, if the separation is increasing, the molecules will go away and it will turn from a solid to liquid to gas. If you are withdrawing heat from the substance, the separation between the atoms and molecule will reduce, and that separation between the atoms and molecules can make the water like gas into a liquid, liquid into a solid. So that was possible. Okay, so heat is lost and heat is gained.
So,
Yeah,
so you have said that ice is 0°C, and when it is heated, it becomes water at 0
yeah,
degrees Celsius.
yes,
Sir, but when you heat it, won't the temperature increase? So won't it become
exactly.
water at like?
So that's what, if now imagine you have ice at 0°, okay, and you want water at 10°. Now it doesn't happen directly. Okay, there is a step 1 and there is a step 2. Okay, step 1 is getting ice to water at 0°. That is a change in state, and this is what I'm trying to get at. So when this horizontal line over here indicate that you continue to supply heat, okay, or in this case where you are taking water to ice, you are withdrawing heat. So heat is either supplied or heat is either lost. Okay, like in this particular case, heat is lost, but there is no change in temperature. There is no change in temperature. Are you
Okay, sir.
following that? Okay,
Yes,
over
sir.
here, heat is supplied, but there is change in temperature. So what we will write it down properly over here. So we have water at 10 degrees Celsius. So water at 10 degrees Celsius, and we want it to cool and form ice at 0 degrees Celsius. Okay, so we want ice to be at 0 degrees Celsius. So the first step is water will lose heat and turn into water at 0 degrees Celsius. Okay, so that's the first thing. Water will lose heat and it will turn into water at 0 degree. So water at 10 degree become water at 0 degree. And then what happens is water at 0 degree will continue to lose heat and turn into ice at 0 degree. Okay, so it will continue to lose heat. Now, this loss of heat, we know how to show that. We have done it in the exercise 1. This loss of heat is written as mc delta T. That means suppose if you have 100 grams of water at 10 degrees Celsius, and if you want to make it 0 degrees Celsius, Q will be equal to 100 into 4.2 into 10. Okay, so that will be 4,200 joules. So that much heat will be required to bring 100 grams of water from 10 degree to 0 degree. Now the heat will continue to be lost, okay, and it will become ice at 0 degree. Now this is again Q, but this Q cannot be written like this, okay, because delta T is 0, because it's 0 degree to 0 degree. There is no change in temperature. Okay, so we will see in this part how to represent this, okay, what to write over here. But this is a very important thing that you should understand, that whenever there is a change of state, there is heat is either taken or heat is either lost, but there is no change in temperature. Okay, is everyone clear with that?
Yes, sir.
Okay. So then generally students have this question: when heat is taken or heat is lost, there is an indicator, and that indicator is change in temperature. Okay, a change in temperature. So example, when heat is taken, there is a rise in temperature. When heat is lost, there is a drop in temperature. Okay, however, when this happens during change in phase, there is no change in temperature. Okay, so obviously the question arises, where is the heat going? Okay, the heat that is lost or heat that is gained during that process, where is that heat going? So the answer is, this heat is used to change the potential energy. Okay, it is used to change the potential energy. That is called as what? Separation between the molecules of the substance. Okay, so therefore the separation between the molecules of the substance is changed. Now again, I'm using this word change because I'm talking about both the things. Okay, whenever there is water to ice, the separation is reduced. Okay, the molecules are coming closer. And whenever there is ice to water, there is a separation between the molecule is increasing. Okay, so heat is supplied for that and heat is lost in this particular case. So there is no change in kinetic energy. So therefore there is no change in temperature. So there is only change in potential energy. So that happens during this phase change. Is that clear to everyone? Okay. Now,
Yes, sir.
yeah, the heat lost or gained during during this change is not manifested as change in temperature. This heat is hidden. Okay, it is called as latent. Latent heat means the heat, whatever is hidden because it is not shown as change in temperature. Okay, and you calculate that heat as m into L. Okay, where m stands for mass and L stands for specific latent heat. Okay, that's the word, specific latent heat. Now what is the meaning of specific latent heat? So suppose for
So can you
example,
just scroll up, please?
yeah, specific latent heat of ice is 336,000 joule per kg. Okay, joule per kg. Now what is the meaning of that? If you have ice at 0°C and you have 1 kg of ice, okay, and if you supply 336,000 joules of heat energy to ice, you will get water, okay, which is at 0°C, 1 kg of water you'll get. So is that clear to you? So remember one thing, if you have 1 kg of water, okay, let us say at 30°C, and if you are supplying 4,200 joules, then you will get 1 kg of water at 31°C. So that 1 degree rise, okay, in temperature, that is called as specific heat capacity, that is given by the letter small c. But here we are talking about specific latent heat. So what is specific latent heat? You have ice, okay, which is at its melting point, that is 0°, and you supply the heat equivalent to the specific latent heat. The complete ice will melt to water. Okay, the temperature doesn't change. So you are going to get water, 1 kg of water. If you supply heat equivalent to its specific latent heat of fusion, okay, then it changes from ice to water. Now the opposite is also true. In your refrigerator, if you keep 1 kg of water, say at 20°C, it will become 0°C and Q will be equal to mc delta T. Now that you have 0 degree of water, 1 kg, then it will turn into 0 degree of ice, okay, which is again 1 kg. Now in doing that, water has to lose 336,000 joules. Okay, if that much heat is lost, then the water temperature, the water will change its state to ice. Is that clear to you? Okay, so we are going to continue this. So here is latent heat, the word capital L. So it is the amount of heat required to change the state of a unit mass. That means 1 kg. Okay, the amount of heat required to change the unit mass substance, okay, either from solid to liquid or liquid to solid. So the heat that is either lost or gained to turn from solid to liquid. So when you are supplying that much heat, it will go from solid to liquid. If you are withdrawing that much heat, it will go from liquid to solid. Fine. So any questions you have?
No, sir.
No,
Okay.
sir.
Now, this is definitely a big value. Okay, so one can understand. So there are some questions before we go to something like this. Say if you have 1 gram of water at 0°C and you have 1 gram of ice which is also at 0°C. The question asked is, which of the two has more heat energy? Which of the two has more heat energy?
So
What
1
do you
gram
think?
of water.
Why do you think so?
So because water will need more, no, sir, I think it'll be ice because ice will need more heat. Ice will need more heat.
Need more heat as in, okay, say for example, there are these two people. Okay, this is person A and this is person B. The question is, who has more money? So one has to check the amount of money they have. Like suppose A has 50 rupees, B has 80 rupees. So you know that if you want if to have A the same amount of money that B has, you have to give him 30 rupees. Are you following that? Okay. So therefore
Yeah, sir.
B has more money. Now, if you are going to apply a similar logic to this point, so here you have water at 0° and ice at 0°. So say for example, if you want to bring one of them to the state equal to the other,
So
if
ice
you
will
have to
require more
supply,
heat.
yeah,
Ice will
so
require more heat.
right. So therefore, you will have to supply 336 joules to ice. Okay, you have to supply 336 joules to ice. Okay, then only ice will become equal to 1 gram of water at 0°. Okay, so therefore, this has more heat. Okay, 1 gram of water at 0° has more heat than 1 gram of ice at 0°. Right. Okay, so similar questions can be asked to you. You should be able to answer. So again, just having a small recap of what we have done. We have done the change in states. We have also seen where is the heat used. It is used to change the potential energy. When I say potential energy, what do I mean? The separation between the molecules. Okay, that also we have seen. We have seen, the cooling curve. Okay, and the heating curve. Okay, and we had also discussed latent heat. So amount of heat required by a unit mass to change its state is called as the latent heat. Now, what we have after this is, like we did in the earlier exercises, some natural consequences where there is high specific latent heat of fusion of ice is used. Okay, so I'm not going to write down, but we will just discuss that. So number one is, all the snow on the mountain doesn't melt at once. Okay, again, if it is a 2-mark question, the first thing that you are going to say that ice has a high specific latent heat, that is 336,000 joule per kg. Okay, then you have to get the second mark, by explaining how is that a reason, because that much heat will be required to melt 1 kg of ice. And since it is a lot of heat and there is a lot of ice that covers the whole mountain, all of it will not melt at once. And if the question is asked, how is that benefiting? So obviously, then you have to write the reason that if all the snow melt at once, that will flood the river and the area, the land, and that will be a problem. So that is in a way good that all the snow is not melting at once. Okay, we have already, your general knowledge tells you that if the glaciers are melting, the rise in sea level is happening. So there are places which were earlier uh, land are now under the water. Okay, so we don't want that to happen continuously. Okay, then other things like uh, why do you add cubes of ice to a cold drink? Okay, so instead of making a cold drink in 0-degree water, why do we add ice to it? Okay, so the answer is clear from this question as well. When you add a ice cube, each gram of ice, okay, when it melts, it takes away 336 joule of energy from the cold drink. Okay, and a cold drink, which is just like imagine it to be water, when it loses 4.2 joules, 1 gram drops the temperature by 1 degree. Okay, so therefore losing this much heat will definitely bring down the temperature. Okay, so I repeat again, the first point is to state that water has a high specific latent heat of fusion, and the second point is to explain that give reason. Okay, third commonly asked question is, it is generally much cooler after the hailstorm. Okay, because whenever it is snowing, the snow covers the whole area, but when the snow starts melting, that means it is absorbing heat from the surrounding, and therefore the temperature around the surrounding will drop further and it will be much cooler. Okay, so this
So
gives you
basically, for
the,
the answer to all these give reasons, like the main point should always be that the specific latent heat of fusion of ice is 336 joule per gram, right?
right, right. And the second point is to explain that due reason. Like in exercise,
Yes, sir.
we had water has a high specific heat
So it's
capacity.
the natural
Yeah,
consequences, right? All those
yeah,
five.
yeah, yeah, yeah.
Yes, sir.
Okay, so what you don't have in this exercise is point number 11.15. Okay, you have 11.16. This is not included, and 11.17 is also not included. Okay, and
Okay, sir.
even the heating curve. So like I
So
told
we
you,
only have the melting curve.
cooling curve.
Yeah, sorry for the interesting
Yeah,
one. Yeah.
so that is something which is very clear in the syllabus also. uh, Only the cooling curve is included, right? Okay, and in the textbook, sorry, in the syllabus also, it says that uh, cooling curve of water. Okay, so that we have to be careful about. So it can be of any other substance also. Uh, it can be of any other substance. That's fine. I mean, they will give you, say for example, if I ask you that this thing, wax has a melting point at 80 degrees Celsius. It is cooled to 10 degrees Celsius. Draw a cooling curve. Okay, now you can say that it is cooled to cooled from 100 degrees Celsius to 10 degrees Celsius. Draw a cooling curve. So for this, what will you do is, suppose you have something like this and you make the markings. You start at 100. You can show this as 80 and this as 10. So you can bring down the temperature till 80. Then at 80 degrees Celsius, you just show the horizontal, and from 80 to 10, you are again dropping the temperature. So this can be done. Of course, you write temperature and time over here. So that
So
will
can
be
you
the,
repeat why 80 will be like a standard line? Is it because its melting point is 80?
because that is the melting point. Okay, what is the meaning of melting
Okay,
point?
sir.
Wax which is at 100 degree, it will lose the temperature, become 80, and this wax is in liquid state over here. Okay, now this is a change of phase that happens, and wax will be solid at that point. So this time, okay, in this time, from time whatever, suppose this is seconds, so this is 5 seconds, this is 10 seconds, 15, 20, 30, 35. So between 10 seconds to 20 seconds, the temperature of wax continued to remain 80, whereas wax continued to be cooled. That means wax continued to lose heat. But that heat that is lost, that means it is losing potential energy and not kinetic energy. And therefore, wax is turning from liquid to solid. Okay. So now we will
Yes,
see
sir.
the numericals.